The primary goal of qualitative analysis is to provide a rigorous and in-depth interpretation of qualitative data. Collaborative qualitative analysis can achieve the two goals by engaging multiple researchers to code collaboratively and converge on consensus interpretations through iterative discussions. Based on grounded theory and thematic analysis, researchers have identified a 6-step procedure to ensure a CKA process is performed well, including preliminary organization and planning, open and axial coding, development of a preliminary codebook, pilot testing the codebook, final coding process, and finalization of the codebook and themes. However, for graduate students, early career researchers, and diverse research teams, strictly following this prescribed workflow to achieve rigor and depth can be challenging due to the time and labor costs. This is because CK usually requires multiple rounds of iterations to resolve disagreements, and CK also contains complex and detailed procedures, for example, whether and when to perform independent open coding, and how to form a final consensus via iterations. We introduce CollabCoder, a lower barrier, rigorous workflow that streamlines the collaborative qualitative analysis process. CollabCoder assists multiple researchers to generate code collaboratively, adhering to the key inductive stage of grounded theory, named Phase 1, Individual Open Coding, Phase 2, Merge and Discuss, Phase 3, Codebook or Code Group Generation. Prior to formal coding process, CollabCoder ensures that all coders can access the same data units and perform data interpretation at the same level among coders for efficient discussion. CollabCoder allows users to identify open codes on a shared platform while maintaining coding independence. With the coding assistance with LLMs, it can generate a list of open codes for data units. CollabCoder also provides centralized data management and synchronization within the coding team. CollabCoder also facilitates deeper and high-quality discussion via a shared workspace. It also aims to generate cost-effective, fair coding decisions and achieve fair user engagement. Lastly, with these code decisions, it can enhance coding efficiency using a top-down approach to generate code groups. Now, let's take a look at how CollabCoder supports two coders, Alice and Bob, to perform a CK process smoothly. Phase 1. Independent open coding. When Alice adds codes, she can click on a cell and input her own code, and CollabCoder will suggest two kinds of suggestions, including summary and relevant codes from codebook. Alice can choose a code and edit it as needed. She can add keyword support will be shown beside the code. She can also add her certainty level between 1 to 5, and also edit the individual codebook. Phase 2. Merge and discuss. To access each other's codes, two coders must both have completed 100 of their tasks. All information are listed side by side, including original data, certainty level, original codes, as well as the keyword support. CollabCoder supports one-click calculation of similarity and integrator reliability. By examining the similarity of code pairs, filtered the agreements and disagreements. Using quantitative metrics, Alice and Bob can start discussion and propose a code based on their coding information. If Alice and Bob cannot agree on a code pair, they can request suggestions from ChatGPT, which will provide 3 alternative final codes based on the original codes and text. This ensures two coders' codes are considered. After selecting a suggestion, they can do further customization and editing. After generating a final code decision, the user can replace the original codes, leading to updated similarity and higher integrator reliability. Coders can continue to resolve for those code pairs with poor similarity. Phase 3. The final code decisions will be listed on the interface. Users can generate code groups from scratch. Drag the codes into groups. Refer to original data. They can also create code groups by GPT and do further editing as needed.